in here, but we deal with the nomenclature, that is how to name compounds, and students that miss this class for whatever reason, this class and the next one, they just struggle with that stuff all semester. Even though we keep going through that, there's just something about being here today for this particular topic that seems to make a big difference. And for those that do have difficulty with the material today, don't forget that I do record this stuff as well. And so if you do need to go through things and review again and again, do so. But don't let yourself become a statistic of my experience with students in the past. If you're going to become part of a statistic, make it a good statistic. Okay. The other thing I'll say is that when we do this stuff here in nomenclature like we're going to be doing, the students that do get it tend to get 100% on it. They do really well. And students that don't get it, it's not like you get 50%, you get like 0%. So you will want to be sure that if you're not understanding it, that you ask questions as we go along. Now, as far as the answers go, I am a person that is of the belief that I do not go through answers to exam questions in class. If you do have questions on those, however, the way that I can help you is individually. I don't like to waste the time with people that have done well in here, because if you've done well, then it's just wasting 10, 15, 20 minutes of class time to go through that. And rather, I can go one-on-one with somebody in my office on office hours to help the person out that's struggling in here. The other thing I'll do, but you'll need to remind me after class, is I will post the answer key out on the bulletin board. I forgot to do that here before class, but if you remind me right when we get done today, I believe I have the answer key with me. I do. And then I'll post it up on the bulletin board across the hall, and you can take a look at it over there. So, but by and large, I was pleased with the results on this exam. If you're wondering what the scores mean as you look at it, you're going to see two scores in a circled score. The score out of 69 points is the score that you received on the multiple choice portion of the exam. To arrive at that score, took your multiple choice score and multiply that by 3, since they were each worth 3 points apiece, and then represented that as a score out of 69 points. The score out of 31 is the score on the handwritten portion of the exam. To arrive at that score, what was done was, you'll see a number on the bottom right-hand corner of that page. That number was subtracted from 31, and that is the number wrong that you got on the handwritten portion of the exam. And to arrive at this number on the bottom, I've summed together the numbers on the little corners on the two handwritten pages. So like this one here was a 0 and 6, so I summed together 0 and 6 to get the 6 points on the front, and then subtracted that from 31 points. And then I took the two scores, the score out of 69 and the score out of 31, summed them together to get a score out of 100. I do this all in my head, and I do it very fast. Occasionally I make mistakes. I don't do it often, but occasionally I do. So if you're concerned about the math, do please ask if you have any questions on that. So, are there any questions? Yes, ma'am.
Is the number at the bottom of the page number wrong, right?
Yes, the number at the bottom corner is the number wrong on that page, except for the front page. And then again, the one on the front page is the sum of those two on the third and fourth. So whatever you see on the front, if it says 8 on the front, that means you probably got 4 plus 4 or 5 plus 3 wrong on the two handwritten pages. Anybody else? Yes? They were worth 3 points apiece. Anybody else? All right, you had a question waiting for you today when you came in on the Socrative app. And let's go ahead and check that out. It was to give the proper name a compound that has the formula of K2O. And it looks like, oh, well, somebody said phosphate. But potassium oxide is correct. And somebody said dipotassium oxide. We haven't learned about those prefixes di, tri, or whatever yet. Again, remember that the metal retains its name. The nonmetal retains its root name, onto which we add a suffix of IDE. Check out the next one. Now, Work with your neighbor if you need to on this. It says, what is the correct formula of calcium fluoride? You probably need to get your periodic table out for this one. So get your periodic table out. See if you can remember how to arrive at those formulas. If you didn't pick up a worksheet at the very beginning, you can come and pick up your worksheet.
Can I pick up the
After class you may. So check out your answers here, talk them over. Okay, get your answers locked in. Let's take about 10 seconds. 5, 4, 3, 2, 1. Correct choice is B. It's CaF2. Now, in case you've forgotten how that works, remember that we need to determine the charge based on position in the periodic table. Calcium is right here, which means its charge is always going to be 2 plus. Fluoride is over here, which means its charge is always going to be 1 negative. If we take a 2 positive and a single negative, how many calcium ions do we need altogether? How many fluoride ions do we need? Right. And because we need 2 fluoride ions to balance the charge of the 1 calcium, we then write the formula as CaF2. Remember that the subscripts are a count of the number of atoms in the formula. Any questions on this one?
Does it matter that it's a diatomic?
Good question, because that often comes up. It actually doesn't matter that it's diatomic. The only time that something matters when it's diatomic or not, if it's an element by itself. And so fluorine by itself has a formula of F2. But when it's a part of a compound, then we use the charges, actually part of an ionic compound, we use the charges to arrive at the formula. So good question. Anybody else? All right. So then, we left this middle portion of the periodic table empty the other day, and we did not put any charges in on here. And the reason for that is because the elements in the middle have what we call variable charges. I'm color coding this here so you can tell the difference between them. The ones that I've shown blue are ones that have fixed charges, and the ones here in red we're showing have variable charges. Now, by variable, that means that you do not need to memorize what those charges are going to be. The reason for that is if you look at the name, for example, if you would see Fe with a 2 plus charge, not the name, but if you saw the formula, or if you saw Fe with a 3 positive charge, the name of these respectively would be the iron 2 ion, and this would be the iron 3 ion. And these represent the Roman numerals 2 and 3 respectively. And so iron, because it's one of the elements contained here where we have variable charges, could sometimes have a 2 positive, sometimes have a 3 positive. And you don't need to memorize that iron has those 2 possible charges. You just need to know that iron is one of them that has 2 possible charges. Likewise, if we looked at something like these names, and can you see where the Roman numerals come from? Where do you think the Roman numeral 2 comes from here? The charge, sure. If the charge is a 2 plus, then it's a Roman numeral 2. The charge here is a 3 plus, then it's a Roman numeral 3. So if we then saw the names copper 1 and copper 2, and we wanted to know these formulas, copper 1 would be Cu with a charge of 1 plus, and copper 2 would be Cu with a charge of 2 plus. It's that simple. And again, because copper sits here on the periodic table, right here, it's one of those elements that has variable charges. So any of the elements there that are in the transition elements may have charges that vary. Victoria?
What row 14 and 18? I don't think I like the charge.
Okay. Well, row 18 is really simple. And why does row 18 not have a charge? Well, not so much that there's neutral. Noble gases, right. They're noble gases. And they're called noble gases because they do not react with anything. And we actually know that that's not entirely true. Today we do know that krypton reacts with fluorine, xenon and radon react with fluorine and oxygen, but for the most part they're non-reactive. And the reason why we're not showing charges for the elements of group 4A or 14 is because some of these are metals, some of them are nonmetals. The nonmetals, carbon and silicon, it's very rare for them to form ionic compounds. And for the ones that are down here, which we're going to look at next, I will block these out right here. Notice that I'm color coding it in red. If I'm color coding it in red, that's telling us that these would also have variable charges. And so you say, well, wait a minute. You just said at the top here that it's a 3 positive and this is a 3 negative. Well, that 3 positive applies to pretty much to aluminum and perhaps to gallium. And the 3 negative here pretty much applies to these two. Okay? So then there are some of them that are in the transition elements. There are some exceptions to these. These elements right here have fixed charges. So the ones I'm color coding in blue, again, these have fixed charges. And so all of these in the middle here are variable with the exception of silver, cadmium, and zinc. And now you may remember something that we looked at here the other day, and that is on your table of ions to memorize. You might as well pull them out if you don't have them memorized yet. See, that was which class that we looked at? February 2nd. We had this table of ions to memorize. And you should have noticed on this table of ions to memorize that cadmium, silver, and zinc are 3 common metal ions you were to memorize. And the reason why we are memorizing these 3 is because these 3 are the elements that have fixed charges amongst all of the rest of them here that are variable. So again, that's why these 3 are listed on that table of ions to memorize. Because they have fixed charges when all of the others in the center have the variable charges. So then, when it comes to writing out formulas for these, we could look at a name like iron 3 oxide. And if we want to write a formula for iron 3 oxide, we don't even need to look up the location of iron in the periodic table, because what does the Roman numeral 3 tell us? It's a 3 plus charge. So we don't need to memorize that because the Roman numeral tells us. We do, however, need to look at where the oxygen is located in the periodic table. And oxygen is located right here, so its charge is always 2 negative. Oxygen has a 2 negative charge. So remember now what we'd like to do is we'd like to balance charges. The total of the positives must equal the total of the negatives. Now, when it's not clear like this, and we see a 3 and a 2, we can find what's called the least common multiple. And what is the least common multiple between 3 and 2? 6. So how do we get 6 positive charges?
Add another iron.
Add another iron. How do we get 6 negative charges? Add 2 more of the oxides. So we now have 6 positives balancing the 6 negatives. The formula for this then becomes Fe2O3. Remember once again that the final chemical formula is always written without indication of charge. If you include the charge, it is wrong. If you had a high school teacher that let you keep the charges in there, they shouldn't have done that, because chemists do not write formulas with the charges shown in those chemical formulas. If we had something like iron 2 oxide, the charge on iron 2 is 2 plus. Oxide we saw just above is 2 negative. So if we have a 2 positive and a 2 negative, what happens to the charges? They cancel out, and the formula becomes FeO. And so this here is the formula for iron 2 oxide. Any questions on these two? Okay. Now, like I said, when we look at these Roman numerals will tell the charges for us. And one of the things that's nice about this is that used to be a different way that these were done, and this was just going out when I was a student, but some of this still lingers on in the vocabulary today. The Fe2 positive was formerly called the ferrous ion, and the Fe3 positive was called the ferric ion. The copper 1 ion was called the cuprous ion, and the copper 2 ion was called the cupric ion. Now, of course, these come from which names?
Latin.
The Latin names, right. And if you look at the correlation between them, we see an OUS suffix and an IC suffix. The ion that had the lowest charge had the OUS suffix of the pair, and the one that had the higher charge of the two had the IC suffix. Now, what was confusing about that was that if we look at the names here, the IC in this case is a 3 plus charge. Here the IC suffix has a 2 plus charge. And furthermore, if you compare the 2 plus charges, this one had an IC suffix, this had an OUS suffix. And so what a person used to have to do was we'd have to memorize all of the ions in that middle portion of the periodic table, know their charges, and remember that the highest is always IC, the lowest is OUS. You're still going to see this somewhere. For example, when my boys were born, my ex-wife, she used to have to take some iron supplements, and when you went to buy iron supplements, you wouldn't go and look at iron 3 whatever or iron 2 something. You bought it, she would get the iron, what was it, ferrous sulfate, I believe, as one of the supplements. So there are still some things where when you look at the names, those common names still exist. But chemists, for the most part, have replaced them with these Roman numerals as a means of naming those compounds. If we look at another example here, let's take something like titanium. Now, you do need to know your Roman numerals in order to succeed with this. Let's say we had something like titanium. And what is this Roman numeral here? 4. So let's say we had titanium 4 sulfide. We want to write this formula. Well, the symbol for Ti, or for, yeah, there it is. Titanium is Ti. The charge would be 4 plus. Sulfide would be S with the charge of 2 minus. And again, we would get the sulfide based on its position in the periodic table. We'd see that 2 minus charge. And now, like before, to write the chemical formula, we want the charges to balance. So we could do it like we've done here with just basically comparing charges, or by doing the least common multiple. And this is where sometimes students will get this wrong. What is the least common multiple between 4 and 2? 4. It is 4. And how many titaniums do we need to get a 4 plus charge? 1. How many sulfides do we need to get 4 negatives? 2. So the formula of this compound becomes TiS2. And so this would be the formula of titanium 4 sulfide. Now going in the reverse direction, again, I can just keep going here. If you have questions, you'll need to stop. Raise your hand, whatever. Let's say we want to go in the reverse direction. We have CuO and Cu2O. And now we want to come up with the names for these. Now to come up with the names, one of the things that you should realize is where copper is located in the periodic table. Copper is located right here, which tells us that its charge is going to be variable. And if its charge is variable, that means that in its name we need to include the Roman numerals and the parentheses. So we can just start though leaving out the Roman numeral. So leaving out the Roman numeral, we would call the first one copper oxide. Leaving out the Roman numeral, the second one would be copper oxide. They'd both be copper oxide. But now we want to fill in what that Roman numeral would be. So take about a minute here, discuss with your neighbors, put those Roman numerals in there, and see what you come up with. Compare your answers. Who's here? Let's check out the answers. First one is going to be copper 2. Good. So here's copper 2. The next one would be copper 1. Now in case we had trouble with that, where does this Roman numeral come from? The charge. So in working backwards on this one, you'd have to realize that oxide always has a charge of 2 negative. And if we look at the formula, how many atoms of each do we have? 1. So if we have 1 of each, that means that the charge has to balance on this one, and the charge must be 2 plus. And this charge, once again, is where that Roman numeral comes from. And then likewise for the second one, if you know that oxide is 2 negative, that must mean that if we have 2 copper ions and the charges are balanced, the charge on each one of these must be 1 plus. And again, this charge here is what determines the Roman numeral on the name. Yes?
Is it always going to be oxide, or could it be like oxide, or like different subjects?
Well, you must know what we're discussing next. Okay? Because right now we haven't learned about anything with 8. If we have, these are the category of binary ionic compounds. And in binary ionic compounds, the first element always retains its name, and the second element retains its root name, onto which we add that IDE suffix. But we're moving on next to the 8s. So any questions on these? Okay, so now on page 139 in your text, now you don't have to open it. If you can follow along without opening it, that's fine. But those that do and want to look at it, I want to point out some stuff that we looked at here the other day. If you've not memorized your sheet of polyatomic ions, get your polyatomic ions out so we can look at that here as we go through and compare these. Now, we talked about this the other day, but if you look at this list of polyatomic ions that I had you memorize, most of these here have a suffix of 8. Most of them have a suffix of ATE. And what do all of them here that have a suffix of ATE have in common?
O or 0.
Yeah, negative charge, and which element? Oxygen. Right, they have oxygen. and they always have a negative charge. Now, there's some of them though, which even though we don't have them written here, you're going to be expected to know, and that's why I have you look at page 139. You do not need to know all of them here on page 139, but if you memorize the nitrate ion, I would expect that you also know the formula of the nitrite ion. And if you memorize the chlorate ion, I'd expect you to know the formula of the chlorite ion. And if you look at these, and we'll look at page 139 here right now. We check out 139 and see how these compare. Notice now when we compare the formula of chlorate and chlorite. How does the formula of the chlorite ion compare to the chlorate ion? One less oxygen. How does sulfate and sulfite compare? Sulfite has one less oxygen. How does nitrate and nitrite compare? Yeah, which one always has one less oxygen? Ite does. And so I remember mentioning this to one of my classes, but an easy way to remember this is that the one with the ATE suffix, ate one more oxygen. And so that's an easy way to keep it straight. It ate one more oxygen, so it has one more present. And so, again, if you know the one that has the ATE suffix, then you should be able to come up with the formula for the one that has the ITE suffix. Which then takes us to the next Socrative question. And the next Socrative question on here is, what is the correct formula for the phosphite ion? Now you're not going to find that in your table, but compare your phosphate and your sulfate and sulfite, nitrate and nitrite, and see if you can figure out the formula for the phosphite ion. Talk it over here if you need to. Take about a minute. Maybe you don't need a minute. It's getting quiet in here. So we'll take maybe about 10 more seconds. Get an answer locked in here. We'll go 5, 4, 3, 2, 1. Correct choice is letter A. Because remember, if it has an ITE suffix, it always has one less oxygen than the ATE suffix. So if you memorize the phosphate ion, and that's really the key to it, you have to memorize the phosphate ion. If you memorize this one here, then the one that has the ITE suffix has one less oxygen. And how does the charge compare? Same thing, exactly. Charge doesn't change. The only thing that changes is the number of oxygen. Now, simply because we put a suffix of ITE on there, for many of them, doesn't mean that they're always possible. For example, you are to memorize the carbonate ion. And the carbonate ion has a formula of? With a 2 negative charge. But if you wanted to write the formula for the carbonate ion, you can't do it. You can't do it. There is no such thing. Okay? Now, some of them there are such a thing, some of them aren't. Of course, some of you might be a fan of which show? Big movie. Another version just came out right before Christmas. Star Wars. And if you're a fan of that, now I'm not a huge fan of it, but if you are a fan of it, you might remember that Han Solo in the very first one was encased in carbonite. But there's no such thing as carbonite. Okay? And then there was like the song 3 Days Grace, I think, that had the Kryptonite, the Superman movie, and Superman was got his power from the kryptonite. There's no such thing as kryptonite either. So because we can put an ITE suffix on it doesn't mean that it's always real. So just don't get fooled by Han Solo and Star Wars. All right, so next up, if we want to write formulas, let's say that we want to write a formula for something like potassium nitrate. Now when you see the ATE suffix on there, the ATE suffix, now of course we don't need to be texting during class. Remember, if you're a texter you should be sitting in the back row. All right, so if we are wanting to write a formula for potassium nitrate, we should remember that the ATE suffix tells us that it has oxygen in there, and it's on our list of ions to memorize. Now if you haven't memorized it yet, you have your sheet out, which is the NO3 with a single negative charge. And then we want to combine that with potassium ions. Potassium, we come up with this formula based on its position in the periodic table. So its charge is 1 plus. So if we have a single positive, nitrate is NO3 with a charge of 1 negative. And again, you get that based on its position here in the periodic, not this position in the periodic table, but this is your to memorize one. We then try to balance charges, and the formula would become KNO3. We have a single positive charge that balances a single negative charge. Formula is simply KNO3. So we try to balance charges just like we did before. If we want to do something like this, let's say we want copper 1 carbonate. Copper 1 carbonate. To come up with this formula, what does the Roman numeral 1 tell us? 1 plus charge. This is copper, so it's Cu with a single positive. The carbonate suffix tells us it contains oxygen. And this is from our list of ions to memorize. Remember, you memorized the 8s. So if you haven't memorized them yet, look it up. Formula for the carbonate is CO3, charge is 2 negative. So now if we want to balance charges, which one do we need more of? And how many more? 1 more. So now we have 2 positive charges balancing the 2 negative charges. Formula for copper 1 carbonate is CO2, Cu2 CO3. Any questions on this one? Okay, let's try this one. Let's try aluminum acetate. Aluminum acetate. I've heard some call it acetate before, but it's acetate. So aluminum. Now this is one that we get based on its position in the periodic table. Aluminum would have a charge of 3 plus. You see the ATE suffix, which tells us it contains oxygen, and that means it comes from your to memorize list. So this is the most complex formula you're memorizing. Its formula is C2H3O2 with a single negative charge. Now to balance charges, which one do we need more of? Acetate. And how many more acetates do we need? 2 more. So we have C2H3O2 with a single negative, C2H3O2 with a single negative. So then when it comes to write the formula, how many aluminums do we have? 1. And what do you think we do if we have 3 of these acetate ions? Put it in parentheses, and then the 3 outside. So, remember now that these are called polyatomic ions. And that means they are many atomed ions. And whenever we have more than one of a polyatomic ion, we have to place it in parentheses and a subscript outside. These up here, we did not include parentheses. Don't put them in. We don't include parentheses because how many carbonates do we have here? Just one. How many nitrates do we have here? Just one. So parentheses are not included in these. The only time that they are included is when we have more than one of a polyatomic ion. Once again, if you had a high school teacher that let you put parentheses in and didn't mark it wrong, that was wrong with that person. The only time that the parentheses are included is if there is more than one of a polyatomic ion. Any questions? Okay, let's look at another one here. Let's look at magnesium hydroxide. Now this one throws some students for a loop because many will see the IDE suffix and think that because it has an IDE suffix on it that it must be a monoatomic ion. However, if you look back to your list of polyatomic ions, you're going to see two of them on here that have an IDE suffix. One of them is the hydroxide ion, the other here is the cyanide ion. The cyanide ion here does not have any oxygen in it. Hydroxide, though, is one of those exceptions. It is the only polyatomic ion that we're learning that has an IDE suffix that also contains oxygen in it. Sometimes I'll see some students just either give the oxide ion or something with the hydrogen in it, neither of which is correct. Just think of the name hydroxide as hydrogen and oxygen in its formula. So if we want to write the formula for magnesium hydroxide, we go back to the periodic table, see that the charge on magnesium is 2 plus. The charge on the hydroxide ion formula would be OH, single negative charge. Now we like to balance charges, which means we need how many magnesiums? 1. How many hydroxides? 2. So now, to write the formula, we would put Mg, parentheses, good. And then in parentheses OH, and outside the parentheses, the 2. And remember, whenever we have more than one of a polyatomic ion, that we place that polyatomic ion in parentheses and a subscript outside. This is probably the type that I see the most mistakes on. Biggest mistake I see is something written like this. Okay, and if it's written like this, it's telling us that there's 2 hydrogens but only 1 oxygen. So this is an incorrect way of writing that formula. We have to show the 2 oxygens and the 2 hydrogens, and to maintain its identity as the hydroxide ion, we place it in parentheses. Any questions yet? We're kind of progressing to more difficult here. Oh, by the way, calcium hydroxide, magnesium hydroxide, this is the stuff found in milk of magnesia. If you've heard of milk of magnesia before, it is used as an antacid. An antacid. It's one of the ways to neutralize acid in the stomach. This one here, calcium chlorite. Now notice that this one has a suffix of ITE. The suffix of ITE now is not on your list to memorize. And it's not a monoatomic, because if it's monoatomic, then its suffix would be IDE. So, if we see ITE, what does that tell us?
One less oxygen. Chlorate.
One less oxygen than the chlorate. So, that means you would have memorized that the chlorate is ClO3 with a single negative charge. So the chlorite must be ClO2 with a single negative charge. So then to write the formula for this, we go back to the periodic table. We see that calcium has a charge of 2 plus. The chlorite ion has a formula of ClO2 with a single negative charge. Which one do we need more of?
Right.
Chlorite. How many more? Just the one more. So now we have two positives balancing the two negative charges. The formula for this one then becomes Ca parentheses 2. Any questions on this one here? Okay, so let's try out a couple more here. You do these. I'm not going to put these on the Socrative app right now. Let's try Na2CO3. And let's try, we haven't gone this direction yet. Maybe we should go this direction first. Na2CO3. Now to come up with a name, we simply put the names of the ions together. Sodium carbonate. And you get the carbonate ion based on its formula right here. So this is sodium carbonate. If we see something like this, FeSO4, and this one here, Fe2SO4, in parentheses, 3. And we want to arrive at names of these. Well, these happen to be ones that I have in some vials. At least I thought I did. Here's one. Now, of course, I thought I had the other one. And that must mean that it's somewhere here on my cart, doesn't it? And finding stuff on my cart is a big task, so I won't be able to pass it out here today. Because it won't make any sense with just one of them. Okay, I thought I had two of them. All right, well, let's try this out. First of all, if we see Fe, we have to remember that iron is one of them that has variable charge. It's a variable charge. That means when we write its name, we have to include Roman numeral. So it's going to be iron something sulfate. And the second one here is going to be iron something sulfate. So to figure out what that something is, or the Roman numeral, we kind of need to work backwards. So we need to know what is the formula and charge of the sulfate ion. SO4 with a charge of 2 negative. And so you're going to see that right down here at the bottom. It's SO4 with a 2 negative charge. So we then look at the formula and we see how many irons are in this formula. Just one of them. If there's only one of them, that must mean that the charge on this iron would have been 2 plus. And so the name of this then would be iron 2 sulfate. Whereas if I went to the next one, again the sulfate has a formula of SO4 with a charge of 2 negative. But how many sulfates are we showing in the formula? 3 of them. And each of those sulfates have a charge of 2 negative. How many irons are we showing in the formula? 2. So what must the charge on these irons be in order to balance the 6 negatives? 3 plus, exactly. So 3 plus makes a total of 6 positives. So that means that this one has a name of iron 3 sulfate. So we kind of need to work backwards on this one to arrive at what those Roman numerals would be. Now if we're dealing with a positively charged polyatomic ion, for example, something like the ammonium ion, let's say we have something like NH4 in parentheses 2S. you need to recognize this polyatomic ion as being this one right here. This is the ammonium ion. And as the ammonium ion, we would then call this one here ammonium sulfide. And it's an IDE suffix because how many elements are represented in this part of the formula? Just one. There's no oxygen attached. If oxygen is attached, then it would be sulfate or sulfite. But there's no oxygen with this, so that means that that portion of the name is simply sulfide with an IDE suffix. So any questions on that one there? Okay. Next then we're going to look at, and this will be our last one of the day, and then we're going to get some practice. We'll look at binary molecular compounds. Binary molecular compounds. And in binary molecular compounds, we just review what binary molecular means. The word binary means it contains two elements. If it's molecular, those elements must both be nonmetals or metalloids. So there's no metals present in the binary molecular compounds. So an example of something like this would be ClF3 or P2Cl4. To name these, here's what the rules look like. The first element, we say retains its name. The second element in the formula retains its root name, onto which we add a suffix of IDE. And then what we do, in fact, if we stopped at this point, the rules for binary ionic and binary molecular would be identical. Okay, and this is why it's important for us to look at and ask ourselves, and that's why we started, is this an ionic compound or is it a molecular compound? And so the difference with these is we say that Greek prefixes are added to indicate the number of atoms of each element shown in the formula. Now these Greek prefixes are shown in your text on page 145, but I can sum this up for you real easily. And most of these, I would say, are ones that you know already. So we need to know the prefixes from 1 through 10. And those prefixes are, respectively, mono, di, tri, tetra, which might be new to many of us, penta, hexa, hepta, octa, nona, and deca. So think like decade for 10 years. Or an octagon, which is the shape of a stop sign. Or a hex nut. which is a little thing that you screw on when you have nuts and bolts. The hex nut has a 6 side. The Pentagon in Washington, D.C. has 5 sides. Triangle has 3 sides. So now, again, these prefixes are added on to indicate the number of atoms of each element. Usually the prefix mono is left off. It's included in some rare cases. If it is included, it's usually included with the second element. So, that means the name of this first one would be chlorine trifluoride. Chlorine trifluoride. The next one would be diphosphorus tetrachloride. Diphosphorus tetrachloride. If we look at this one here, SF6, this would be sulfur hexafluoride. If we go in the reverse direction, let's say we had something like diarsenic pentaiodide. Well, now we don't even need to look up charges because this is non-metal to non-metal. They don't have charges. We simply look at the prefixes. So we would have AS2 and penta means 5. And which element would we have? Iodine, so it would be I5. We saw something like this. Tetraphosphorus decoxide. And yes, I did spell this correctly. Don't ask me why we have these rules. Whenever the prefix is adjacent to oxygen, the letter A is left off. So like if we have penta or tetra, like in the case of penta, we wouldn't call it pentaoxide, we'd simply call it pentoxide. So letter A is left off whenever it is adjacent to oxide. So if it's tetraphosphorus, this is going to be P4O10. And if you wanted to write the name N2O4, this one here we would call di what? Dinitrogen tetroxide. Remember, the letter A is left off whenever that prefix is adjacent to oxygen. Any questions on any of these that we've done here? Yes?
How do you know if it's a binary molecular compound?
Okay, good question. How do we know if it's binary molecular? Let's say that we looked at this formula right here, AlCl3. Is this an ionic compound or is this molecular? And how do we know?
Because of the aluminum.
Because of what?
The aluminum.
Because of the aluminum. If it's ionic, it has to be metals with nonmetals. If it's a molecular, it would be nonmetals with nonmetals. So this is where it tricks. I'm glad you asked that question because this is where it kind of trips some of us up. So now if we look at this and we say that this is an ionic compound, specifically a binary ionic compound, and we wanted to write its name, the name of this would be aluminum chloride. Good, aluminum chloride. Not aluminum trichloride, because the prefix tri would only be included if this is a molecular compound. So before writing the formula, you actually have to ask your name, is this ionic or is it molecular? Because the prefixes are only included with the molecular compounds. And what I say, though, sometimes is that people, once they learn these prefixes, they become prefix happy. They want to use the prefixes all the time. But you have to remember, before you start naming, ask yourself, is it ionic or is it molecular? All right, let's practice these. And these, we're going to wrap up with, I think, about 10 or 11 on the Socrative app. And these are ones that you will get to practice. If you see the formula, write the name. If you see the name, write the formula. And I'm going to put these up here in order. I'm going to give about a minute for each one. Yep. So the next one, the first one is up on the Socrative app. First one is up on the Socrative app. Discuss your answers. Again, I'll give about a minute for each one. And if you get the answers, work ahead. All right, I'll give you 5 seconds to lock in the first one. If you want to work ahead on these, you can work ahead on these. So, we'll go 5, 4, 3, 2, 1. The correct answer here is the one that most of us have, and that is disulfur hexabromide. Disulfur hexabromide. Next one is NiCl2. Again, if you want to work ahead, I'm going to give about a minute on each one of them. Here's the others you can work in on. Get the next answer for the NiCl2 entered into the Socrative app. 4, 3, 2, 1. Correct one is choice D. We need the Roman numeral in there because nickel is one of those elements that has variable charges. Variable charges. And you can't do the nickel dichloride because the prefix di must mean that it's a binary molecular compound. Proper chemical name of Ca3, PO4 in parentheses, 2. This one here you're going to, I'll hide these answers for right now. You can work ahead if you already entered in your answer. We'll go 5, 4, 3, 2, 1. Oh, creative names there on some of them. But the correct answer is calcium phosphate. Calcium phosphate. This is one that has your ionic compound with your polyatomic ions. So it's calcium phosphate. Proper chemical name of Ag2, CO3. Does it have a fixed charge or does it have a variable charge? Fixed or variable? 4, 3, 2, 1. And the correct answer is silver carbonate. No Roman numeral because silver is one of those that has a fixed charge. Don't remember, that's one of, don't remember or do remember. Sulfur has that fixed charge. Okay, next up, we have the Cr2. This one's a multiple choice. Cr2, in parentheses, SO4, 3. Let's go 5, 4, 3, 2, 1. Correct choice is chromium 3 sulfate. This is one of them where the chromium is one of them that has the variable charges. And it's an ionic compound. So with the variable charges, it has to have the Roman numeral in there. The Roman numeral is a 3, because the charge in the sulfate is a 2 negative. Need to go through these faster here. All right. Next one, we have iron 3 cyanide. Iron 3 cyanide. 5, 4, 3, 2, 1. All right, good choice. Letter A. It's Fe. Oh, and I'll just go next. Fe. And then parentheses Cn. Outside the parentheses a 3. Next is lithium nitride. Be careful on this one. I've mixed up your naming methods. So this is not something we covered today. This is from last Tuesday. 5, 4, 3, 2, 1. Correct choice is letter E. It's Li3N. And the reason why it's that is because lithium has a charge of 1 plus. Nitride is N with a charge of 3 negative. So that must mean we need 3 lithiums to balance the charge of the 1 nitrogen. Next one is possible, so you can ignore the choice that says this one is not possible. In case we've forgotten, we can actually make compounds of some of the noble gases. The xenon tetroxide. We'll go 5, 4, 3, 2, 1. Correct choice is letter B. Good. I just told you it was possible. Okay. Next up, magnesium chlorite. Look at the suffix, chlorite. 4, 3, 2, 1. Correct choice is C. And I think I have one more left up here. Ammonium acetate. 5, 4, 3, 2, 1. Choice A is correct. The next one is not up there, but, oh, hold on. No. Go. Anybody know this one? Cocoa Puffs. All right. Way to go. We'll see you later.